All right, 7.2. So in 7.2, we're going to talk about a technique called integration by parts. So this is a really cool technique, and it tells us what to do in scenarios where you're dealing with the product of two functions. So you're trying to integrate something like f of x times g of x. A couple of you have gotten in trouble over this, right? Because you keep thinking that integral of f of x times g of x is just integral of f of x times integral of g of x. Like you can just distribute the integral across that multiplication, and you can't, right? You can't. But here's what is true, right? So if capital G is an antiderivative for lowercase g, then the integral of f times g is f times capital G minus the integral of f prime times capital G. Okay? That's maybe a little bit of a confusing way to write it down. In practice, when we're actually using this technique, the way that we usually write it is we let u be one of the functions, and then we let v be the other function. Or rather, we let v be kind of, we choose u and then we choose dv is what we actually do. So we choose the thing u is going to be the thing that we differentiate, and dv is going to be the thing that we integrate. But anyway, when we make those replacements, then this is what the formula becomes, right? Integral of u dv is u times v minus integral of v du. Again, it's a little confusing to look at it like this, but in practice, I think it'll become more clear when we look at some examples. But before we do that, I wanted to prove that this is actually a true statement. And by the way, I'm labeling this statement 2. Basically, your book labels this statement as statement 2, and I wasn't sure if in the homework it was going to say something about, use statement 2. But this is what they mean when they say statement 2, and this is what they mean when they say statement 3, if it comes up in the homework. But anyway, so here's the proof, right? So to prove this statement, we're actually going to start off by differentiating f of x times capital G of x. Now, we know from the product rule for derivatives that this is going to be derivative, or the first times the derivative of the second plus the derivative of the first times the second, right? Now, capital G was an antiderivative for lowercase g. That means the derivative of capital G is just lowercase g. Right? So we get this. Now, that implies that this thing right here is an antiderivative for f of x times capital, or sorry, other way around. This is the derivative of that. That means that this f times capital G is an antiderivative for this, right? So in other words, if you integrate this thing, you should get this thing back. Well, so then solving for the integral of f of x times g of x, right? Integrals do distribute across addition, so we can distribute the integral across that addition and then move this part over to the other side, right? And then you end up with the statement that we began with. So anyway, so there's the proof. Let me walk you through a couple examples of using integration by parts. And as I walk through these examples, I'll give you some pointers about how to choose u and how to choose dv. In other words, how to choose the thing you're going to differentiate and how to choose the thing that you're going to integrate. So let's integrate a few things. Let's do integral of x cosine x dx. So x times cosine x. Notice first and foremost that a u substitution is not going to help you here, right? You can try any kind of u substitution you like. You can do a u substitution. You can let x be u. That's not going to do a single thing. You could let x be, or u be cosine x, but then the derivative of cosine is negative sine, and I don't see a negative sign anywhere. You could let u be the entire thing. Let u be x times cosine x and see where that leads you. It's not going to get you anywhere, right? So this is an integral that, as of so far, we cannot integrate, right? We don't have the tools for it. But integration by parts, that's the tool that we need to do this. So here's, because we have a situation where we have one function times another function, and yeah, integration by parts will help us here. So I'm going to let u be x, and I'm going to let dv be cosine x, right? So in other words, u is the thing that I'm going to integrate, that I'm going to differentiate. dv is the thing I'm going to integrate. So if I differentiate u, then I get du equals dx. And if I integrate dv, then I'm going to get v. Sorry, I should have said dv is cosine x dx is what I should have said. Now if I integrate this, I'm going to get v equals sine x, right? And now what does the formula say? The formula says that this integral should be u times v minus du times v. Or in other words, minus the integral of v du, right? So integral of x cosine x dx, right? In other words, this is just the integral of u, and then cosine x dx was dv. Well, the formula says that this would just be u times v minus the integral of v du. In other words, it would be x sine x minus the integral of sine x times du, sine x times du, which is just dx. And notice that what's happened now what's happened now is that the thing that we have left to integrate is easy to integrate, right? It's not a product like what we started with. It's just, we just have to integrate sine x, right? So antiderivative of sine x would be negative cosine x, right? So we'd get x sine x minus negative cosine x plus c, right? Or in other words, x sine x plus cosine x plus c. Okay? Now, you can verify this by differentiating, right? If I differentiate this, I'm going to get, oh goodness, I'm going to get x times cosine x plus 1 times sine x. So, oh man, so I get x cosine x plus sine x, and then the cosine x, its derivative is negative sine x, and the derivative of the constant is just going to be 0. And sure enough, those are gone, and boom, you've got x cosine x, just like what you started with. So yeah, so this thing works out, right? A couple things that I want to point out. When you make this little thing over here, you can almost think of it like a chart. You can think of it like a chart. And in fact, I'm going to do this explicitly on some of the problems we look at later on. But you can kind of think of it like a chart. Like, this is the thing that you're going to be differentiating. So I don't know, you can put a D for differentiate. And this is the thing you're going to be integrating. So put a little integral sign there. And then when you go to combine them, I usually don't write this step. I find it confusing, right? So I usually don't write this step at all. Usually what I do is that when I'm thinking about this chart, I draw little arrows. I say, well, I'm going to multiply this times that, and then I'm going to multiply this times that, right? I don't know why. That's just helpful to me. Well, and actually, you'll see that it is pretty nice to think of it this way. But when I do this times that, I'm going to keep it positive. When I do this times that, I'm going to make it negative, right? And then I'm able to skip this step and just jump straight here, right? So I would have x sine x minus integral. And when you do this kind of horizontal move, then you do have to integrate. So this is just x times sine x, but then this would be minus the integral of sine x dx. Okay, and so I just jump straight to this step. That's usually the way that I do it. So that's one comment that I want to make about this, and I'll show you that again with another example. But another comment that I want to make is, how did I know to choose x to be the thing to differentiate rather than integrating it? Well, so look, let's try it out. Let's see what happens if we let u be cosine x, and then we let dv be x dx, right? And remember, this is what we're dealing with to begin with. Okay, so if we do things the other way around, we can still differentiate this. Du is going to be negative sine x dx, and then v is going to be x squared over 2, right? And then notice when you do that little trick, u times v, well, that's not a problem. That's just x squared over 2 times cosine x. But then v du, this part, you're going to have to remember, this is the thing. This is the last row is the thing that you have to integrate. So you'd have to integrate now. You'd have to integrate x squared over 2 times sine x dx, and that's even worse than what you started with, right? It just makes the problem worse. So generally speaking, if doing if you're trying to do integration by parts and you end up with something worse than what you started with, then probably you made the wrong choices. Okay, so we don't want to do it this way. What we want to do is do something that's going to make the thing that we have to integrate simpler than what we started with. So a general rule of thumb for picking your u's and your dv's is to use the acronym LEAT or LEOT. I don't know, it's kind of weird. But here's the acronym, right? So you're going to use LIATE. It's like late, but with an I in front. Or, I don't know. Anyway, but LEAT. Okay? And what this stands for is, L stands for logarithmic functions. I stands for inverse trig functions. A stands for algebraic functions. T stands for trig functions. And E stands for exponential functions. Okay? And now, what good does that do you, right? Well, the way that you use this is that you're going to let u be the function whose category comes earlier, right? So, in other words, if you had some kind of integral where you had like an I and an E, then so if you had an inverse trig function times an exponential, you'd want to let u be the inverse trig, and then you'd let dv be the other part, right? Or if you had an integral that was like TL, right? It was of the form TL. L comes before T in this acronym, right? So in other words, if you had a trig function times a logarithmic function, you'd want to let u be the logarithmic function because it comes first, and then you'd let T be dv, right? So you'd let the trig function be the dv part. Okay, this maybe doesn't always work, but it's a pretty good rule of thumb. This is how you pick your functions. So you let u be the function whose category comes earlier in Lee8. Okay, so that's the general rule of thumb. So if you can just remember Lee8, that'll help you kind of determine which function should be u and which function should be dv. So let's give you an example of that, right? So let's integrate x e to the x dx. Okay, so remembering Lee8, right? Here we've got an algebraic function, right? X is just an algebraic function. E to the x is obviously an exponential function, right? So if you're thinking about Lee8, a comes before e, so we should let u be x, right? And that means dv is going to be e to the x dx. Okay, so then you differentiate. Du is dx. V is just, well, integral of e to the x is just e to the x, so that works out pretty nicely. And now you do this little thing, right? So integral of x e to the x dx is going to be x times e to the x minus the integral of e to the x dx. Do you see how nice that is now? Right? This integral is super easy to evaluate, right? It's just going to be x e to the x minus e to the x plus c. And that's all there is to it. Again, you can check that by differentiating to make sure that it actually works, but it should work. Okay? So that's the idea. Lee8 will tell you what function to let u be, right? It's the one that comes first in the acronym Lee8. Okay. Again, that's just a general rule of thumb. You could run into a situation where you have like a trig function times a trig function, and then it's like Lee8 isn't helpful, right? Because they're both the same type of function. But anyway, and then you could end up with a situation like this, right? So let's say that we want to integrate ln of x. This isn't even the product of two functions. This is just one function. But it's a function that we don't know how to integrate yet, right? But differentiation by parts will help us here, right? If you want to think of this in terms of Lee8, what you could think is like that this is 1 times ln of x. And you can think of 1 as being an algebraic function, right? So we have an algebraic function and then a logarithmic function. Well, but then in that case, that doesn't really work out, because then you'd let u be dx, which you don't really want to do. So I don't know. Lee8 doesn't really help you in this in part C. What you want to do is this: you let u be natural log of x, and let dv just be dx. Okay. So now you differentiate, and you get du equals 1 over x dx. And here you integrate, you get v equals x, right? I don't know what I just said. Integrate here, differentiate there. Okay, and now the integral of ln of x dx is going to be x times ln of x, okay, minus the integral of x times 1 over x dx. Oh, that's not bad at all, right? That's x ln of x minus the integral of, the x's here will cancel and just give us dx. So in other words, that's x ln of x minus x plus c. And there you go. Again, you can differentiate that to make sure that it actually works. Okay, but it does work, and so anyway, this is a very nice nice technique. Integration by parts is very good. Another thing that I want to point out to you is that you may have to do integration by parts multiple times in order to get something that you can actually integrate. Okay, so you may have to do integration by parts multiple times. Okay, so let me give you an example. So let's evaluate the integral of x squared e to the negative x dx. Okay. So here I've got an algebraic function, and here I have an exponential function. So if I'm thinking about Lie8, I would let u be the algebraic function, right? So I'm going to let u be x squared, and I'm going to let dv be e to the negative x dx. Okay? So then du is going to be 2x dx, and v is going to be negative e to the negative x. Okay? Now, integral of x squared e to the negative x dx is going to be x squared times negative e to the negative x. So in other words, negative x squared e to the negative x. And then minus the integral of 2x times negative e to the negative x. So negative 2x e to the negative x dx. Okay. Now, that is not, I mean, it almost looks like, it doesn't look more complicated than what we started with, but it also doesn't look less complicated than what we started with. But that's generally kind of like a, maybe it's not a good sign, but it's at least a neutral sign. It's like we obviously haven't gone wrong yet. And if I just focus on this thing by itself, I know that I can solve it by integration by parts. So I should just do integration by parts again. First, let me fix up the signs. So this is negative x squared e to the negative x plus, well, I can pull out the 2, I suppose, and call it integral x e to the negative x dx. So I'm going to do integration by parts just for this piece here. Okay? So just for that piece there. Okay? So maybe I'll do this in a different color. Okay? So for that piece, I'm going to say let u, again, be the algebraic function x. In fact, I'm not going to say let, because that's just going to clutter up my picture, but I'm going to say let u be x, and let dv be e to the negative x dx, right? Then du is going to be dx, and v is going to be negative e to the negative x. And then that tells me that the integral of x e to the negative x dx is going to be u times v, that's negative x e to the negative x, minus the integral of v du, so that's negative e to the negative x dx. Okay, well, this negative and that negative will cancel. Integral of e to the negative x is negative e to the negative x, so this is going to be negative x e to the negative x minus e to the negative x plus c. right? So that's just the green part over here. So now I can finish up the original integral. So integral of x squared e to the negative x dx is going to be negative x squared e to the negative x plus 2 times this integral, which is this thing here. Negative x e to the negative x minus e to the negative x. And then we'll just say plus c, right? Okay, so I can distribute the 2, but we're done now, right? This is negative x squared e to the negative x minus 2x e to the negative x minus 2e to the negative x plus c. And there's our integral. Now again, you can differentiate this to see if you end up back here where you started. You should, right? You should, I mean, I don't mean you should check it. You can check it if you'd like, but if you check it, then you should end up back here, which is pretty incredible, right? So it's again, a very nice technique. I love integration by parts. Okay, let me show you how I would organize this differently, okay? Because this is kind of like it's a little confusing organized this way. So let me show you how I would organize this slightly differently, okay? I'll do it. I'll just redo it. So I'm gonna do example 2, but this time I'm gonna do it differently. I'm gonna do it arranged as a table. We call this the tabular method. So if you know that you're gonna be doing integration by parts multiple times, then you can arrange your work into a table, right? Kind of like we arranged it over here when we did number 1 part A, okay? And now here's how this works, right? So you recognize that you've got an algebraic function, so you know that that's going to be u. That's going to be the thing that you differentiate. And then you've got an exponential function, so that's going to be the thing that you integrate. And now what you do is you just differentiate this thing and integrate this thing. And then you can think about this last step, right? If I do 2x times negative e to the negative x, and I think about having to integrate that, well, I know that I'm going to have to do parts again, right? So I might as well just do it, right? Differentiate and then integrate. Integral of negative e to the negative x is just going to be positive e to the negative x, right? So the signs kind of alternate there. Now here, if I think about this last row, this is the one that it's always the bottom row that I have to integrate. So now if I think about integrating this bottom row, well, that I can do without having to do integration by parts, right? But I want to show you something else, right? So you could stop there and then integrate this last thing, but here's what's even better. If I go one more step, derivative of 2 is just 0, right? Integral of e to the negative x would be negative e to the negative x. Now this is even better because, again, the thing that you have to integrate is always the bottom row. And if I integrate this, well, that's just 0, right? So that's super easy. Okay? So how does this help me answer the question? Well, you do the same thing that we did here. And you draw diagonal arrows until you get to the bottom row, and then you draw a horizontal arrow. Okay, so I'm going to do this times that. I'm going to do this times that. I'm going to do this times that, and then I'm going to integrate. I'm going to integrate this times that. But of course, since it's multiplying by 0, it's not going to add anything, right? Now the signs here alternate. Right, so here you're going to keep this sign. Here you're going to negate it. Here you're going to keep the sign, and then here you would negate it. So what you end up with when you do this is negative x squared e to the negative x minus, right? You would have 2x e to the negative x, but you have to negate it, right? So you say minus 2x e to the negative x. Here you'd have 2 times negative e to the negative x. So that's a negative 2e to the negative x. And you don't negate it. You keep it positive. So minus 2e to the negative x. And then minus the integral of 0 times negative e to the negative x. Well, 0 times negative e to the negative x is just 0. Integral of 0 is just 0. So this is just plus a constant. And that is your answer. Notice we ended up with the same answer as what we got before, only it takes so much less work to do it this way, right? So much less writing. So tabular method's really nice. Of course, this may lead you to ask the question, like, how do you know when to stop, though, right? Like, if you're doing this tabular method, how do you know when to stop? So let me just say, if you're going to do a bunch of integration by parts, you can make your work easier by arranging it into a table and using what we call the tabular method. You know to stop whenever one of the following things happens, right? Either the derivative column goes down to 0, like it did here, and if the derivative column goes down to 0, just keep differentiating until it gets there, right? And then stop, right? Or if the derivative column isn't going to go down to 0, but you end up with the bottom row that is a repeat of the original integral, then what you can do is you can solve for the original integral. I'll show you an example of that, right? So that's two ways that you know when to stop. Of course, there are other reasons that you would stop. Like if your derivative column isn't going to go down to 0, but you're also not going to get a repeat of the original, but if when you get to that last row and you notice that it's something that's easy to integrate, well, then you can stop as well, right? So you stop when you get to something that's easy to integrate. If you know the derivative column is going to go to 0, just take it all the way down there. And then just be aware of, like, if you have repeats, if the thing you're integrating is a repeat of the original, then also you can stop, right? So let me give you an example, or several examples of these ideas. So let's integrate x squared minus x cosine x dx. Okay, so liate, right? Logarithmic, inverse trig, algebraic, trig, and exponential. This is an algebraic function. X squared minus x is algebraic. Cosine x is trig. So I'm going to let u be x squared minus x. And x squared minus x is a function whose derivatives will go down to 0. So I know I'm going to, the easiest way to do this is to just do a bunch of these differentiations. So I'm going to make my little table. I'm going to put x squared minus x here, and I'm going to put cosine x there. So derivative 2x minus 1, derivative again 2, derivative again 0. The integral of cosine x is sine x. Integral of sine x is negative cosine x. Integral of negative cosine x is negative sine x. And then be careful, make sure to switch the sign. So you do this times this, keep it positive. You do this times that, make it negative. You do this times this, keep it positive. And then this times that is what you're going to integrate, but it's going to go away, right? Since it's just 0 times that thing. Okay, so what do we get? We get x squared minus x sine x. This negative and that negative will cancel, so I'm just going to say plus 2x minus 1 times cosine x. And then here I'm going to have a minus 2 sine x, and then here there's nothing left to integrate, so we'll just say plus c. Okay, that's beautiful, right? I would challenge you maybe to differentiate this and make sure you end up with the original. Okay, but that's that. Here's another one. So let's integrate x squared times the square root of x minus 1 dx. Now here you've got two algebraic functions, so Lie 8 doesn't really help us figure out which one to differentiate, which one to let u be. But I do know, I can think of this as x minus 1 to the 1/2 power. And if I think about differentiating that, I'm going to get, 1/2 times x minus 1 to the negative 1/2, and then I'm going to get, if I differentiate again, I'm going to get something times x minus 1 to the negative 3/2, and so forth. That's never going to go to 0, right? But x squared will, right? X squared will go down to 0 in just a couple of steps. So I'm going to let u be x squared. That's what I'm going to differentiate. Of course, all of this sort of relies on me being able to integrate square root of x minus 1, which maybe I can't do, right? But we'll see. We'll see if I can or can't. So I'm going to try to do x squared here and square root x minus 1 there. So 2x, 2, 0. Here, if I integrate this, it's going to be, this. If I think of this as x minus 1 to the 1/2 power, then I'm going to raise x minus 1, I'm going to add 1 to the exponent, get 3/2, and then divide by that new exponent, which is the same as multiplying by 2/3. Okay? If I do that again, I'm going to get x minus 1 to the 5/2, and then I'm going to want to multiply 2/5 times 2/3. That's going to give me 4/15. Okay, and then if I do it one more time, I'm going to get x minus 1 to the 7/2, and then I'm going to want to multiply 2/7 times 4/15. Well, 2 times 4 is 8, and 15 times 7, oh man, 15 times 4 is 60, and then plus 45, so I think 105. Holy schmoly, is that right? Where's my calculator? Give me a sec. No, I think that, yeah, that's right. That's right. Okay. All right. Now I do this plus this minus this plus this minus. Okay, I get I'm going to call it 2/3 x squared times x minus 1 to the 3/2 power minus 2 times 4 is 8, right? So I'm going to call it 8/15 x times x minus 1 to the 5/2 power. Then I'm going to do plus 2 times 8 is 16, so I'm going to call it 16 over 105 times x minus 1 to the 7/2 power plus c. Okay, and that's that one. All right, so if you can choose something that kind of goes down to 0 for the thing to differentiate, then that'll work out just swell. Okay, let me give you an example where that doesn't happen though. So let's say you've got this scenario. Now, neither of these functions is algebraic. If I differentiate e to the x, I'm just going to get e to the x, e to the x, e to the x over and over and over again. If I differentiate cosine x, I'm going to get negative sine x, and then negative cosine x, and then positive sine x, and then positive cosine x, and it's just going to kind of alternate like that. But neither one of these things is going to go down to 0, which sort of begs the question, well, so, when do we know to stop, right? When do we know to stop? And then the other question is, which function do we differentiate and which one do we integrate? So let's remember Liat, right? So Liat, so L-I-A-T-E, I've got a trig function and an exponential function. Trig function comes before exponential function in Liat, so I'm going to let u be cosine x. That's the thing that I'm going to differentiate. So I'm going to differentiate cosine x because of Liat, and I'm going to integrate e to the x. Okay? Now, how far do I go? Well, let's see. If I differentiate cosine x, I'm going to get negative sine x. If I integrate e to the x, I get e to the x. At least that's easy, right? So now I'm going to do this times that, and then I'm going to integrate this times that. So if I integrate this times that, I've got negative e to the x sine x. That's not exactly a repeat of what I started with. So let me go another step. So if I differentiate negative sine x, I get negative cosine x. And if I integrate e to the x, I get e to the x. Now I'm going to do this times that, and I'm going to integrate this times that. If I do that, I'm going to have negative e to the x times cosine x. So there's my repeat, right? So I'm going to stop there then. So I've got plus, minus, and then I'm going to integrate this thing. Okay, so here's what I've got. This is going to be e to the x cosine x minus negative e to the x sine x. So that's really plus e to the x sine x. And then plus the integral of negative e to the x cosine x dx. Okay, so in other words, this is e to the x cosine x plus e to the x sine x minus integral of e to the x cosine x dx. Well, notice that this is the same thing as that. So what I can do is I can add this to the other side. In fact, let me kind of write it out like this. So I'm going to rewrite it. So I've got integral of e to the x cosine x dx equals e to the x cosine x plus e to the x sine x minus the integral of e to the x cosine x dx. So if I add this over to the other side, then I get 2 times the integral of e to the x cosine x dx equals e to the x cosine x plus e to the x sine x. Okay? My task was to find the integral of e to the x cosine x, and what I found is 2 times that. Well, so then obviously I can just divide both sides by 2, and so I get integral of e to the x cosine x dx equals e to the x cosine x plus e to the x sine x over 2. And of course I have to have a plus c at some point, right? I should have probably had a plus c here and a plus c there. But there you go, right? So that's that answer. All right, so you know when to stop when either the derivative goes down to 0 or the last thing that you're integrating is easy to integrate, or when the last thing that you're integrating is a repeat of the original thing you were trying to integrate, right? So that's how you know when to stop when you're doing this tabular method. Okay, one last example. Okay, for definite integrals, we're just going to evaluate the indefinite integral, and then we'll plug in the limits of integration at the end when we're finished integrating. So let's look at an example of that. Sorry, that's supposed to be tangent inverse of x dx. So that's supposed to be a negative one. So it's tangent inverse of x dx. Again, this is a function that we, as of right now, we don't know what the integral of tangent inverse is. But we can use integration by parts to figure it out. So now this isn't a product of two functions, but that's okay. You know, we can do the same thing as we did. Remember when we integrated natural log? Sorry, I was trying to find it. When we integrated natural log, we just let u be natural log, and then we let dv be dx. So let's try the same trick here. Let's let u be tangent inverse of x, because we know what the derivative of tangent inverse is, right? So we'll let u be tangent inverse of x, and we'll let dv be dx. And then we can make a little table out of this, if you like the tabular method, right? I shouldn't have put a line there. I should have the d up here and the integral up there. See, my problem is that I already know how this plays out, so I know that it's a one-step thing. But anyway, derivative of tangent inverse is 1 over 1 plus x squared. Integral of this thing is just going to be v, or in other words, x, right? If I continue to try to differentiate this, it's not going to get any nicer, right? It's not going to go down to 0, and neither is this thing. So I'm just going to stop there, because this last, if I do this times that, and then I integrate this times that, I'm going to have an x over 1 plus x squared, and I can do a u substitution there. That's like a natural log type of situation, right? So I'm going to add this and subtract that, and I'm just going to go ahead and stop there with the integration, or with the tabular method. So here's what I end up with. Integral of tangent inverse, and I'm just ignoring the limits of integration for now, but integral of tangent inverse of x should be x times tangent inverse of x, right? X times tangent inverse of x, minus the integral of x over 1 plus x squared dx. And now we can do a u substitution, right? Let u be 1 plus x squared. Then du is 2x dx. So I can put a 2 there and a 1/2 there. And I end up with x tangent inverse x minus 1/2 times the integral of 1 over u du. Well, that's just x tangent inverse of x minus 1/2 times the natural log of the absolute value of u plus c, I suppose. Okay, so I'm going to get x tangent inverse of x minus 1/2 times the natural log of the absolute value of u. What was u? U was 1 plus x squared. Oh, I can drop the absolute values then, because 1 plus x squared is always positive anyway. Okay, and then plus c. So So then to do the definite integral, then we would say, well, so then the integral from 0 to 1 of tangent inverse of x dx would just be x tangent inverse of x minus 1/2 times the ln of 1 plus x squared, evaluated from 0 to 1. Okay, well, if I plug in 1, tangent inverse of 1 is pi over 4. Pi over 4 times 1 is just pi over 4. So I'm going to get pi over 4 minus, if I plug in 1 here, 1 squared is 1, 1 plus 1 is 2. Ln of 2 is, it's not very nice, it's just ln of 2. So I'm just going to have minus 1/2 times the ln of 2. Okay, now if I plug in 0, 0 times whatever is just going to be 0, so that's fine. Here, 0 squared is 0, 1 plus 0 is 1, ln of 1 is 0, so I'm just going to get 0 minus 0. Okay, well, so there's your answer. I've run out of room, right? But it's pi over 4, so it's pi over 4 minus 1/2 ln of 2. Ugh, is your answer. You could plug that into your calculator. I found my calculator. Pi over 4 minus 1/2 times the ln of 2. So it's about, 0.44 or something. But anyway, so that's that. So that's how you would take care of those situations.